Hello and welcome to this lecture of the course Elements of Mechanical Vibration, having discussed the displacement transmissibility and the base excitation case. In today's lecture we are going to get introduced to the force transmissibility in more detail. Okay. So, the point here is to figure out what FTR expression is. Okay. So, what is this x of t for a given force f naught e to the power j omega t? We know that this is the governing equation of motion, very well known, we have done that many times. And so, what is the response to this governing, what is the solution of this governing equation of motion? You assume a harmonic solution because there is only one frequency e to the power j omega t is the excitation function, and therefore, we have already solved this, and then we know that very well that this is the amplitude of vibratory response f naught over k divided by square root of this entire term. This is quite familiar to you. Now, x dot from this solution is again very well known. If you take the time derivative, this is what the x t is and this is what the x dot t is. Okay. What do you use it for? Now, if I want to know how much is the force transmitted, what shall I do? I will now focus on this foundation, the base, okay, and treat it as a free body. We will not worry about what is happening to this mass now, that basically is obtained as x of t, right. Assuming that this is rigid enough or heavy enough, the force going into the ground, okay, will be how much? It is the force which is getting transmitted through the spring and also the force which is getting transmitted through the dashpot. Those are the two forces which are going to be pushing the foundation or will be acting on the foundation. Now, because this is assumed rigid enough, that means there is no motion of the base or the foundation. The stiffness or the restoring force is only dependent on the absolute x value, the response value. Okay. So, the stretch in the spring is going to be x t, and it is unlike the base excitation case where where the base was assumed to move and then we found out the spring force to be k into y minus x, but in this case this is assumed rigid and almost like a fixed one, and therefore, the force getting into the ground or the base or the foundation is going to be k x for the spring and c x dot for the dashpot, because the dissipating force in the viscous dashpot is proportional to the velocity x dot t, and the constant of proportionality is the damping coefficient c. Is that clear now? So, both these two forces are going to act simultaneously on the foundation, and therefore, the total force getting into the foundation FTR is going to be vectorial sum of the two forces, or you may write it this way, but x dot t is going to have this phase with respect to the displacement, right. Coming from this j, this can always be written as omega x as the velocity amplitude e to the power j omega t minus phi plus pi by 2, that is the phase between the displacement and velocity. So, the displacement will have amplitude x, the velocity will have amplitude omega x, and so they are both these two forces are 90 degrees phase apart, as we have already seen, right. So, this is how the transmitted force is to be obtained. Now, obviously, the force transmissibility is the ratio of the transmitted force to the induced force F naught. So, what are we going to do is to write this expression transmissibility ratio as equal to force transmitted to force induced, which is the input force in the mass F naught, and we know that FTR was written like this. And so, if I replace this FTR by this expression and also replace this x of t, this response is nothing but what? x, capital X e to the power j omega t minus phi, and C x dot was written like this. These are the two expressions, and now if you want to expand this further, I will replace capital X again by the expression that we already know for a harmonic excitation case. You know, this is already seen in the previous slide. So, now if I replace capital X as well in this particular equation, then I get the expression after doing some algebraic manipulation which we have been doing in the past. We will end up getting the expression like this. So, basically what you will have to do here is write this as k sorry. So, when you replace this x with f naught by k, you will essentially get this as f naught, and e to the power j omega t minus phi will be common and can be taken out, and so you will have plus j c over k, okay. F naught will be again constant. So, this is going to be like 1 plus j c over k and c omega over k, in fact, because these things will be c omega and then k is coming from this side. So, that multiplied by e to the power j omega t minus phi. So, this is all going to be the numerator, and then you can solve this to get an expression like this. So, the numerator by resolving this or writing this as square root of 1 plus c omega over k, I mean, because this is a complex quantity, you can write this as 1 plus c omega over k whole square, and you know how to replace c omega over k. So, you can show that this actually turns out to be 2 zeta r, right. So, this is something which we have already done once. So, I would leave it to you to work this out, that this indeed turns out to be this, and of course, then there will be some phase, additional phase here, which will get absorbed here in this particular case. So, there will be some one phase here j alpha or so, but that phase gets added into this phase. So, because most of the times we are more concerned about the amplitude or the magnitude of the transmissibility ratio. So, we will at the moment ignore what is going to be the exact expression for the phase angle. Okay. So, it is all going to be a little bit of a mathematics for getting substituting x into this expression and getting the expression of the transmissibility ratio. But do you recall that this expression is similar to your base excitation case? So, the displacement transmissibility and force transmissibility, both the two expressions are actually identical. All right. So, this is how you get the mathematical expression defining the force transmissibility, and the corresponding phi is of course this the variation of the transmissibility ratio is similar to the displacement transmissibility ratio. Obviously, the expression is the same, mathematical expression is the same, and we have seen this graph in the past. But now what I am going to do is to plot this graph in a log scale, and then this is how it looks like. Okay. It does not change the character in the sense that you still have this particular interesting point at square root of 2 or 1.44 below which any excitation force amplifies the force transmitted to the ground, okay, which means that transmitted force is greater than F naught. That is why this amplitude value or the force transmission transmitted is that ratio is more than 1. That is how you can see that if omega is less than omega n roughly, for all the values of operating speed, the transmitted force is more than the excitation force, because this ratio in this range is greater than 1. You can notice that up to this point, all the points on irrespective of the damping in the system, they are all having a higher level of force transmitted to the foundation. Obviously, if we have a larger damping, as you notice here, if you have lower damping, the force transmitted is many times more. As you notice, just for the sake of comparison, you may notice that if the damping ratio is 0.1, let us say if you are operating close to resonance, then if the compressor or the condenser unit has, let us say, 10 Newton of harmonic force generated because of its operation, in the ground it will transmit 50 Newton of force, okay, if the damping ratio is 0.1. And typically even these rubber isolators will not have damping ratio, I mean it will still have 0.2, 0.1 in that range, but even for a larger damping ratio of 0.1, the transmitted force is going to be 5 times the excitation force. Obviously, as you notice, if you increase the damping level, maybe 3 times the damping with reference to this case, 10 Newtons will transmit the force, I mean 10 Newton of excitation will still transmit 20 Newtons of the force in the ground, right. So, you still have double the force going in the ground by a very poor design of the isolation, okay. So, even if the damping is still quite substantial, you can't get the force going in the ground reduced in any way. You can see that as long as you are operating in this region, no matter how you design your isolator having a better damping property, you will still not get a desired effect. But let us see what happens, if this omega over omega n, what is this omega over omega n? It is the frequency ratio, excitation frequency ratio, if this is equal to 5, okay. What does that mean? That this condenser unit mounted on the mounts here, the natural frequency of this entire system omega n, if that omega n is 1/5 of the excitation frequency, you can see that this omega n is omega over 5. Now, if this condenser unit is, let us say, rotating at maybe 1400 rpm, let us say, okay, which means roughly 25 hertz. 25 hertz, 1440 or 1500 rpm, which actually is translating to roughly 25 hertz divided by 5 means 5 hertz of the natural frequency, okay. So, if you have a condenser unit weighing maybe about 100 kg, you will have to use isolators which are such that the omega n, which I am now saying should be about 5 hertz, which is like going to be 1 over 2 pi square root of k over, if suppose the mass of the condenser unit is 100 kg, you can then work that out, that the value of k, effective k that you need is going to be 10 pi square upon 100, right. Yeah, no, multiplied by 100, is it? Yeah, multiplied by 100, not divided. So much of Newton per meter, right, that is effective k. So, if you have 4 isolators, individual isolators will be 1/4 of that. I mean, this is how the roughly the stiffness will have to be estimated for us to design the isolation system properly, so that you are operating somewhere here, but and then if you do that for the same damping ratio of, let us say, 0.1, I am operating with a transmissibility of, let us say, 0.06. 0.06 is the transmissibility ratio, okay. What does that mean? The transmitted force is going to be this multiplied by, if the excitation force is 10 newtons. So, it is still going to be just 0.6 Newton. Compare it with 50 Newton which was getting getting into the foundation. Instead of 50 newtons you are just getting 0.6 Newton. What have you done? You simply made sure that your supports are flexible enough so that the natural frequency of your system is, let us say, 1/5 of the excitation frequency omega. Now, omega here we assume that if it is rotating at 1500 rpm will be 25 hertz. Now, omega which is 1500 rpm, which is going to be 2 pi over 60 cycles per second. (1500 rpm) translates to this, which is going to be roughly 25 hertz, and that is going to be the excitation frequency if you divide it by 5. So, if you take that, you will get natural frequency of 5 hertz. That is how I will design this support. You can see that if you blindly put it on any isolator without understanding what the implications are, you will end up transmitting a much larger force into the foundation. But if you wisely do it by understanding the basic principle here from our vibration theory, you will see that you can design it in such a way that the transmitted force is a fraction of literally fraction of the excitation force amplitude. And in fact, now you can see and realize the problem with the damping, right. The damping, if you chose it to be large enough, yes, you would transmit much lesser force, just 2 times rather than 5 times, right, near resonance, right. But look at what will happen if you manage to get a flexible mounting, but your damping is still 0.3, it will transmit this amount of force in lieu of this level of force. Okay. So, instead of 0.06 times F naught, you are going to transmit 0.15 times F naught, roughly here 0.15, right. So, more than 2.5, I mean roughly 2.5 times the transmitted force with a larger damping. So, what basically you understand from this graph is that if you design the isolators properly and make sure that your operating range is somewhere here, which I have been saying that should be, thumb rule is that R value should be greater than 3. You notice here that damping actually is detrimental, even damping is actually is bad for the isolation, right. And therefore, although we have been told that damping is good, damping should be there, yes, damping is good in a way, but it is good only close to resonance where it matters, otherwise it is bad. And therefore, you should have a calibrated damping in the sense that damping should be just enough to ensure not large amplitudes or large force is transmitted during resonance, but you must have as low a damping feasible so that the transmitted force is minimized in your normal operating range, which is going to be, if you design things properly, it is going to lie in this particular zone. Okay. I hope these things are clear to you now. You will have a large force transmitted during crossing of the criticals, but because you are going to spend most of your time operating the system, lower damping hill here is always beneficial. That is yes.
In most practical cases, wouldn't the structural damping be enough to take care of the limits that we have? Because there is already some structural damping, so the levels will not rise to at resonance and we want low damping after resonance?
Yeah. So the question is, because the structural damping do have reasonable inherent material damping, you do not really need to do anything as such to add any extra damping to the system, because that amount of damping through the structural the material damping that is there in the structures like steel or any construction material, mechanical structural material, that would be good enough. Yes, it will be good enough definitely here when you are operating. The structural damping ratio for steel, as we know, roughly of the order of 0.005 or 0.01 at the most. So, upper limit could be of this order, and so with that you will be really comfortable here. But sometimes if you are coasting up rather slowly for some reasons, if you cannot traverse through this resonance fast enough, then you might end up generating large excitations transmitted to the base, because you notice that even with 0.05 you are almost transmitting 10 times. Okay. So, you can imagine what will happen with 0.01, right, and then some intelligent damping can be designed. So, of course, this is a little far fetched, but it is still realistic that you design your systems so that when you are passing through this region, you activate certain external damping mechanisms. Okay. For example, people have come up with magnetorheological dampers, where by activating a magnetic field or an electric field, the magnetorheological properties of certain material can be used to enhance the damping only when you are crossing this resonance region. So, what will happen is, you are going to traverse this path by activating additional damping in the system, and the moment you cross the resonance you deactivate it. So, you get best of both, right. So, when you have activated the damper, you avoid resonant conditions, and then when you are past that square root of 2, you deactivate it, so that the lowest damping will be quite useful. So, you can then design your system to have this kind of a hybrid damping or an active damping, that damping which is activated only when it is required, right. But then of course, it will add to complexity of your systems and so on. So, as long as you are ready to shell more money in the design, you can in fact develop your own semi-active kind of a system, where certain dashpots which are having interesting properties. So, you basically have probably a constant stiffness, but the damping coefficient is what I call as a modified or changeable damping coefficient. So, the C value gets increased here by activating magnetorheological action, or the fluid which is there in the dashpot, it can be activated through some external activation energy to cause the damping coefficient to rise significantly high, so that only in this period you activate it and generate a large damping, and the moment you go past this particular point, then you deactivate it, so that the least damping works. Okay. And yes, if you can take care of this crossing over the resonance, the normal level of structural damping that we typically get in structures like steels would be reasonably good to get the best benefit of operating in this particular region. So, the long and short of it is damping is good only in certain small region and it is bad in the normal operating range. Okay. So, you should be careful. If you make a statement now, having learned the vibration theory, that damping is sacrosanct best alternative for vibration control, I think you are making a mistake. You are not really making a right statement, an appropriate statement. It is not untrue, but it is also not completely true. Okay. Now, let us take a small example here just to illustrate what we have discussed. It is quite similar to the vehicle problem that we have taken up. So, supposing that this condenser unit is modeled like a mass, we know that if there are multiple rotating systems inside this, as a hypothetical case, what I told you, that maybe there will be a fan here which will be driven by a motor here through a belt. So, the motor will be rotating, let us say at 1500 or 1440 rpm, that is the standard operating speed of an electric motor, and maybe this is rotating at, let us say 750 rpm. Okay. So, then what happens? Because of the unbalance in the fan, you will have one excitation force here and you will also have another excitation force from the electric motor. There is a pulley at the end of that electric motor, whatever are the reasons, there will be some unbalance at the motor end as well. So, you will have two excitation forces here, one whose amplitude is going to depend on the amount of unbalance in the fan, and then there will be another force F2 magnitude of which is going to be dependent on the amount of unbalance in the motor shaft. So, both of them are going to coexist simultaneously. Now, we are assuming that both of them are in phase, but they may not necessarily be in phase. Okay. But with the simplifying assumption that both of them are independent of each other and they are time dependent, and then their amplitudes are different and then the frequencies are different, they act simultaneously on the condenser unit. Now, let us assume that they have frequencies, let us say 100 radians per second and 200. Now, they may be different than those values here, just for the sake of illustration. These two frequencies are, let us say one is double of the first one. Now, what we already know is that with these excitation forces, the mass or the condenser unit is going to shake with some vibration amplitude, and that is going to act like an excitation force. So, this unbalance here at both of these are essentially going to move this this condenser unit mass, and those forces, excitation forces, are going to be like sending these excitation forces to the ground. So, we have to design these isolation pads properly, so that we get a reduced transmitted force to the ground. Okay. How do we do that? We have just seen in the previous slide that we properly evaluate the value of k as well as c. Now, we have seen how k is important. K is important for influencing an appropriate natural frequency, but that natural frequency is related to, related to in the sense it depends upon what omega is. Okay. Omega n is decided or designed to have certain value depending upon what omega is, okay, which will for a given fixed mass, it will only influence what is the value of k. So, when I say isolation pads should be properly designed, it means that you need to design the value of k in a way broadly omega over omega n should be greater than 3. Again, let me repeat, this number is not sacrosanct, there is no formula or proof to say that it is 3, it is just in practice people tend to use this number as some kind of a benchmark. You can have 2.5, you can have 5, as we have seen, higher this value better it is. So, this will decide, if you ensure that this ratio is fulfilled, that will tell you what should be the value of k that you should be taking, and what value of C, because a mount like this is nothing but a combination of a spring and a dashpot. Okay. It has certain damping character and it has some compliance or a stiffness character. Now, the damping should be such that it should be as low as possible, provided your operating speed is more than omega n. That is what we are ultimately going to aim at. So, C, you just have to ensure that it is not too high. Okay. That is what the intention of these two parameters is. So, that finally, we get a reduced transmitted force. Now, we are going to now look at the situation. We have already discussed how are we going to model this particular pad, so that transmissibility ratio, force transmissibility ratio is far less than 1. Okay. It should be fraction. We have already discussed that it was 0.06 or something, and then this transmitted force is going to be much smaller. But however, even if it is small, what is going to happen, that these transmitted force are going to excite the foundation with certain dynamic force. Okay. Now, what we are going to look at is, if such excitations going into the ground, they are going to excite certain other systems nearby. So, you imagine that your factory is manufacturing blades or some which makes use of some grinding tools or some delicate products are being machined, and that would mean that if these excitation forces coming from large machinery which is transmitting much larger forces into the ground, they are going to excite the nearby machines into vibration. So, now what is going to happen, that this base or foundation is going to generate excitation to the nearby machines. So, you have, let us say for an example, you have another machine in the same area, in the same workshop probably, which has its own natural frequency, maybe 100 radians per second. When I say natural frequency, maybe this part can be rigid enough, but then this cantilevered overhanging portion can be a flexible thing, right. So, you can imagine that there is a mass and then there is a cantilevered section. So, this itself will vibrate, and if suppose this natural frequency turns out to be 100 radians per second. Now, we have already declared that there are two frequencies, excitation frequencies, because there are two rotating systems here. So, what will happen, the total force which is going into the ground, if the system is linear, will have components both omega 1 as well as omega 2. So, you will have the force transmitted to the ground, okay, will be force transmitted from the first force e to the power j omega 1 t, and maybe with some alpha 1 force, the phase lag, plus the second transmitted force f t 2 e to the power j omega 2 t minus alpha 2. What does that mean? That there would be two excitation base motions, one with the frequency of omega 1 and another with frequency of omega 2. Is that clear? Now, however small these amplitudes of transmitted forces are, because you have already designed these isolators to the best of your abilities and considering the design, you might have a fraction of these forces going into the ground, but that could be good enough to excite some base motion here, and worst thing will happen if one of the natural frequencies of this system is going to match with the same excitation frequency, right. You must note that the amplitude of vibration x over y or y over x, whatever you call it, suppose base is y, it is going to be 1 over this ratio, right. Let us say if you ignore the damping, what is going to happen? This is going to be the expression for it. When r is equal to 1, what is going to happen? So, it does not matter, I mean it does matter that x, this will be very large value. So, with very large value, even if y is small enough, you still have reasonable large value of x. Okay. So, of course, the amplitude is going to govern by the amplitude of the excitation source, but if you are operating close to resonance, this multiplying factor will be large enough, and therefore, you will still have this vibration reasonably large. Now, what is going to happen? You are trying to manufacture, or you are going to operate this machine for some finishing operation on your delicate structure being generated or manufactured, and if this itself vibrates, if your tool itself starts vibrating, then that vibration is going to create products of bad quality. Okay. And this has happened in one of the factory nearby. There were large number of rejections of the components being manufactured only because there was some heavy forging hammer operating nearby, right, and the isolation was very poor, and that can create trouble. So, the point here is you still now need to take care of the base excitation as well. You have already taken care of the force transmissibility by proper designing the isolators of the source machine here, but your target machine is already with a problem here, and therefore, I will have to redesign so that this excitation amplitude is not causing larger amplitudes in the target machine. So, what you do is you put this machine as well with some isolations. Okay. So, you put this under isolation. What is expected that for the same mass with the original k, which could come from here only, you have put additional k here in series now. Okay. What is going to happen that this k, sorry, this k is going to now get reduced. The effective k of this whole system is going to be reduced because you have put a isolation here, flexible mount here. Flexible mounts means you have a low stiffness. Okay. Now, therefore, the original natural frequency, which was 100 radians per second, do you expect this to get reduced? Yes, you are now, let us say, by proper choice of these springs, your natural frequency drops to 30 radians per second. It is quite possible. For the same mass, you are reducing the value of k and ensuring that the natural frequency gets reduced to a very low value. Okay. Now, when this happens, what do you expect? So, initially when you are operating with the original natural frequency with the damping ratio of, let us say, 0.05, you are operating with the transmissibility y by x of 100. Okay. So, for each 1 unit excitation, even if it was 1 micron, that 1 micron was creating a 10 micron amplitude here, is not it? But now with the introduction of these isolation pads, what have we done? The natural frequency has been reduced by 3.3 from 100 radians to 30 radians per second. So, what will be the frequency ratio? So, original frequency ratio omega over omega n was close to 1. Okay. Now, I have reduced this omega n by 3.3. So, now what will this become? Because this omega n instead of 100 radians per second is reduced to 30 radians per second. So, the revised omega n is 30 instead of 100, right. So, the frequency ratio now is 3.3. So, with 3.3 frequency ratio, my operating point slides from here to somewhere there, okay. And with that, the transmissibility is reduced from 10 to 0.1. So, it is almost like 100 times reduction in the amplitude of the system. Okay. So, all of this is going to create a significant reduction in the transmitted vibration by properly designing the isolator. Now, what you are seeing in this example is both force transmissibility being taken care of and displacement transmissibility being taken care of. Okay. The basic point here again is to operate more than square root of 2. This value is square root of 2. Now, the major question that is different in this particular example is that I have taken care of this excitation frequency because the natural frequency was matching. What happens because of the other frequency, which is 200 radians per second? Yes? So, R, which was 3.3, and what is R? It is basically omega over omega n, is not it? So, in this case it was omega 1 over omega n, that is R 1. What we have done is we have ensured omega n to be as sufficiently small, so that the ratio omega 1 by omega n, which is 100 radians per second divided by 30 radians per second, okay, this is your R 1, is equal to 3.3. Now, will this omega n change for this? No, that is an excitation. Omega n is a constant for this particular system. What will be your R 2 for the second frequency? It is going to be 200, or in fact it is, if I write omega 2 over omega n, which is what, 200 by 30 radians per second, that is your omega n for the system, that is going to be 6.6. Is it good or bad? It is even better, because you are operating at 3.3 here and you say that farther the better, you operate as much to the right as possible. So, what it says here, that is a very important point here, that you need to account for or take care of it for the lowest excitation frequency, and that and all higher frequencies are automatically taken care of. Higher frequencies will be automatically taken care of, because you are going to work further on the right for your higher excitation frequencies. So, here when you have multiple such excitation frequencies in the same system, the moment you take care or design the isolation system with the lowest excitation frequency, you take care of the rest of them, the higher of them. Okay. So, we have already answered this point. Okay. So, the vibration control or vibration isolation strategy, you need to design the isolators based on the lowest forcing frequency. You know that, I mean, we have, if you have 100 radians per second, 200 radians per second, design it for 100, and then it will be fine for the higher ones as well. And as we have been saying, that the natural frequency should be at least 1/3 of the lowest forcing frequency, and that is how for a forcing frequency of 100 radians per second, we have designed the isolators so that the natural frequency of the vibratory system is, let us say, 30 hertz. And although damping is good because it dissipates the energy, you have to be very careful. We have already seen how damping can be problematic for regions discussed in the plot. Okay. So, do not excessively use damping, because it is going to be problematic for most of the frequency ranges. So, it is only good near resonance, and if you take care of resonance you really do not need damping at all. Okay. Of course, there are other situations where you need to have good amount of passive damping to take care of instability issues, but those are the things which are generally not encountered in normal vibratory systems, except when you have very high speed machinery, then the issue of instability can arise, and then some amount of additional damping could be useful. But as long as you are you are clear about what your system is and how much damping it needs, you do not have to use excessive damping in the system. Okay. So, a small topic here on the vibration sensor design, how the basic equations that we have learned for a single degree of freedom system, how this is made use of in appropriate design of vibration sensor. No? So, one of the sensors is seismometer, and you must have heard about seismometers. They measure earthquake induced motion of the ground, and so these seismometers are implanted at different locations, and they basically are expected to faithfully record the ground motion. Okay. Now, in a very crude sense, this seismometer, if you want to know what they actually operate, you can imagine them to be like a spring mass system hung from a frame like what you see here, and this mass have a pointer attached to it, let us say, and then there is a rotating drum that spins at a constant speed. Now, of course, instead of that you can have a pen which is vibrating like this, and the sheet which rolls like that, so that it records the seismograph. But here, for the sake of illustration, you may imagine this drum being rotated with the paper wound over it, and then the pencil or a pen attached to this mass would trace out vibration. Okay. So, what it should trace out? It should trace out the base motion, because if this as a whole sensor is mounted on the ground. So, if this sensor is mounted on the ground and the ground is vibrating, then this frame is vibrating, right, and because of that this is going to be like a base excited system, because that spring mass system is going to vibrate based on the base excitation given, and it will trace out a graph which is what you are seeing on the paper. Okay, so what is the deal here? Our motion, input motion is x, isn't it? That is the ground motion, and what is the motion of the mass? The motion of the mass is y, all right. And what is getting recorded here? Will it be x, or will it be y, or will it be something else? It is going to be y minus x, obviously, because that this x is with which this the drum is also going to move up and down. So, what is getting recorded there is the relative motion of the pencil with respect to the frame, that is basically y minus x. Now, if this graph is to represent this x, then we say that the design is perfect, because our job is to trace out the motion of the ground on the piece of paper here. So, the design of this sensor should be such that the trace out on the piece of paper y minus x should be same as x. Isn't it? If this sensor is to trace out the ground motion, then what is being traced out y minus x should be same as x, then it is a good sensor, then it is a faithful sensor recording what x is being experienced. So, let us look at this. So, I call this y minus x, I represent it as z. So, I am saying that z is the relative motion, and what you essentially record here is z. So, this what is being recorded is actually z, right. Now, I will now write the governing equation of motion of this spring mass system, because that is our sensor. Now, when I do that, is not this like a base excited system? So, we know already have discussed this, no? We have seen few slides back that the governing equation is going to be my double dot plus cy dot plus ky equal to cx dot plus kx. Please revise this, refer to what we discussed for the automobile case going on a wavy road. This is exactly the equation that we got. This is going to be the same one, because you know this frame on which it is hung, this frame itself is moving with x, and this mass, the absolute motion is y, and therefore, if you take a free body mass here and draw the free body and then write all the forces, this is how the equation of motion will turn out to be. Now, I replace this y by the relative displacement z. So, y is going to be equal to what? Z plus x. So, m y double dot will be z double dot, and I will take m x double dot on the right hand side. So, it is going to be this. Now, plus you have what? C z dot plus k z, and then again plus c x dot plus k x already we had, and then you have minus c x dot minus k x. So, basically by rewriting this equation by substituting for z, I am going to get this expression. Okay. This m x double dot should have been minus m x double dot. Okay. Now, what do? I have an impressed ground motion x, and going by all our usual stuff, procedure of writing x as x e to the power j omega t. That means, I am assuming that the ground motion is harmonic. I can assume this to be the base input motion, and then with this assumption I can substitute for x double dot here, and also the corresponding response z is going to be capital Z e to the power j omega t, and then if you want to add some phase because of the damping, you can do that. And then finally, if you introduce that, you basically will, of course, x double dot will then have minus x omega square, and therefore, it turns out to be plus here. So, the magnitude then becomes m omega square x, and of course, instead of e to the power j omega t, if you want to write this as the real part, which is cos omega t. The basic equation becomes this, which is quite similar to the rotating unbalanced case, m z double dot plus or m x double dot plus c x dot plus k x equal to m e omega square e to the power j omega t, or cos omega t if you take the real part. So, is it not the same excitation force as we are getting here? So, it is a case of a rotating unbalanced case, except that epsilon is capital X here. Okay. And because of that, what we have obtained earlier for a rotating unbalanced case, that capital X over epsilon was r square upon square root of all that term which is here. So, we basically get the same expression here. Okay. So, what basically we are obtaining here is the amplitude of the relative motion z. Okay. The amplitude of this relative motion z, which is being traced out on the paper, normalized with respect to the input amplitude capital X, here that ratio is given by this expression, okay, quite similar to a rotating unbalanced case. All right. Now, if I plot this expression, we already know that this is how it is going to look like. This is the case of the rotating unbalanced case. Now, look at what is your expected behavior of the sensor. Would you like to have this z by x equal to 1 or 0? What do you mean by z by x approaching 1 value? What does that physically mean? This is mathematical. The ratio should be, I mean, if it approaches equal to 1 or if it is ideally 1, what does that actually mean? That z should be same as x. Yeah? When z, which is what is being traced out on the paper, is identical to capital X, which means that the sensor is faithfully recording what is being experienced at the base, which is the idealistic condition. That is what the sensor should do, that if it is subjected to base excitation amplitude x, the z which is being traced out on the paper should be exactly as x. True? And from the graph, can you tell me, irrespective of the damping in the sensor, what position on the graph would give me that one value of z by x? As far on the right as possible, because all these graph will tend to go to 1, right. You saw that capital R by epsilon, the amplitude of response in a rotating unbalanced case was coming close to the unbalanced eccentricity, right. So, this is the similar case, z by x is going to approach equal to 1 for a larger value of omega, omega by omega n or r. Now, what is that implied, which means that r should be as high as possible, or which actually means that omega over omega n should be as large as possible, right. What does that mean? Now, supposing the excitation to this sensor is, let us say, 100 radians per second. Let me again take an example, 100 radians per second. For a given excitation frequency, what omega n should be to have this ratio as large as possible? What should be the implication in the design? Omega n, or the natural frequency of this whole system, should be as low as possible. In fact, if you make sure that omega n is as low as possible, it would make sure that this ratio becomes as large for all the frequencies, isn't it? So, based on the lowest frequency which is going to get measured, you can design your k or m and or both to make sure that the natural frequency of this entire system is as low as possible. Okay. So, that is how it is. For z faithfully recording the input x, r has to be too large, which for which this ratio is going to approach 1, and therefore, omega n should be smaller, much smaller than the frequency that you are trying to record. Okay. And therefore, practically or physically, it means that the mass should be heavier and the spring should be softer. Compliant spring and a heavy mass will give you very low natural frequency. Okay. So, ideally this is true, that you should have a heavy mass and a soft spring, and therefore, you will find that most seismometers are bulky, they are bigger in size, and the reason for that is because the mass required is large, because you can't have a too low a spring. What will happen if you have a very flexible spring, whichever mass you put, there will be it will just trickle down like that, the static deflection will be too large. So, for it to properly accommodate that softer spring and a heavier mass, they typically are bulkier and a bigger in size. So, to counter these large amplitudes, because the natural frequency is small enough, you add of course some amount of damping to this particular system. Now, look at this, will it going to really matter if the damping is larger or smaller? It does not matter the performance, right. So, just to ensure that too much of amplitudes are not there, the damping is reasonably introduced there, so that to counter very large amplitudes as such. Well, so this is how the seismometers are designed. You understand the basic principles behind the designing of the seismometer, and we are going to look at now how an accelerometer, which is another kind of a vibration sensor, how are they designed. I mean, basically for them it is all again single degree of freedom system, and the basic equations and the basic things that we discussed, the same is at play for their design. So, therefore, it is very important to understand single degree of freedom system in and out, to be able to understand the basic the philosophy and the design principles involved. So, this is the summary of this lecture. Force transmissibility is investigated in more detail, and how we can take care of higher excitation frequencies during the course of design of the isolation system, followed by an introduction to vibration sensor design. How the seismometer design is essentially born out of the basic or fundamental theory of forced vibration. This is something which we discussed in today's lecture, and in that sense how the stiffness and mass parameters of a typical seismometer should be calibrated to get the best accuracy in the measured data. These are a couple of questions that you can answer based on the content covered in today's lecture. These are the answers.